This is the first of two reviews for the final exam. Our final this semester will be worth 200 points, but it'll be the same length as any other tests that we have had this semester. It will cover material from the entire semester, which means every single exam we've had, and it'll be broken down 20% from exam 1, 20% from exam 2, 20% from exam 3, 20% from exam 4, and 20% from exam 5. You will have a final homework assignment, which will be due the day of the final, which will provide you practice problems to prepare you for the final exam. I made the final exam first, and then I made the final homework assignment after that to make sure that the final homework assignment provided you practice with everything you need to do and know for the final exam itself. The final homework assignment does have answers at the back, so as you go through all the problems, you can check to see if you're getting it right. And if you can do everything there, you will be ready for the final itself. Today, what we're going to do is we're going to practice material that came from exams 4 and 5. Exam 4 was based upon chemical reactions and stoichiometry. And the first thing that I'm going to give you a chance to do is to write balanced net ionic equations for several different potential reactions. So what I'm going to do is I'm going to give you a reaction, and then you can go ahead and pause, try to write out the reaction you can that is given in net ionic form, and then tune back, and then we'll go through the answer. First one, I'd like you to write the balanced net ionic equation for barium metal being added to hydrochloric acid. This is an example of an element reacting with a compound, which is a replacement reaction. Replacement reactions, the active element, which in this case is barium, will kick hydrogen out of the hydrochloric acid. When it does that, the barium will bond with the chloride to form barium chloride BaCl2, and hydrogen is given off as hydrogen gas. This is an oxidation reduction reaction. The barium on the reactant side, elemental barium metal, is made up of barium atoms. When it turns into a positive 2 ion, it can now bond with the chloride ions. So the barium is going from a charge of 0 to positive 2, which means it's being oxidized. That means in the replacement reaction, the hydrogen ions, the hydrogens that are +1 in the hydrochloric acid, have to be reduced to elemental hydrogen, and that's why the product is elemental hydrogen made of hydrogen atoms, which tend to bond together to make diatomic molecules to be more stable, instead of hydrogen ions as a product. With this balanced molecular equation now, we have two substances that should be broken up and written as ions to make it more realistic. That is the strong acid HCl and the soluble ionic compound barium chloride. So to write the reaction in ionic form, it should be the elemental barium solid plus 2 hydrogen ions aqueous plus 2 chloride ions aqueous, distributing the 2, yielding a barium positive 2 ion aqueous, 2 chloride ions aqueous, and the elemental diatomic hydrogen gas. The 2 chloride ions are identical on the left and the right side of the equation, so they'll cancel out, leaving the net ionic equation Ba solid plus 2H plus aqueous yields Ba2 plus H2 gas. Next reaction I'd like you to do is to try to write the balanced net ionic equation for solutions of iron 3 nitrate and sodium sulfide being mixed. This is a reaction between two compounds, and the way you predict the products is you switch their partners. This is an example of a non-oxidation reduction reaction. The two compounds already contain ions, and those ions are stable, so all they're going to do is switch partners to see if different pairs of ions will form something that's more stable, which will be either a precipitate, water, or a gas. When you switch the partners, you'll get iron 3 sulfide, Fe2S3, and you'll get sodium nitrate, NaNO3. The sodium nitrate is soluble in water from either the solubility rule number 1 or 2, but the iron 3 sulfide is insoluble from rule number 5. Sulfides precipitate with all cations in all water solutions, except for with alkali metal ions and ammonium. So therefore, the iron 3 sulfide is a precipitate, and because you formed either a precipitate, water, or gas, a chemical reaction is occurring. We have 3 things in our balanced equation that are soluble ionic compounds, so those need to be written in their dissociated forms. Using the coefficients appropriately, the first substance would be 2 iron 3 ions plus 6 nitrate ions. The second reactant would be 6 sodium ions plus 3 sulfide ions. On the product side, the precipitate stays bonded together, which is why it's a precipitate. And then the sodium nitrate should be dissociated into 6 sodium ions and 6 nitrate ions. In this reaction, the 6 nitrate ions and the 6 sodium ions are the same on the left and the right side of the equation, so they cancel out as spectator ions, leaving the final net ionic equation 2 Fe3 positive aqueous plus 3 S2 minus aqueous yields Fe2S3 solid. Third and final reaction I would like you to write a balanced net ionic equation for is the reaction of silver metal being added to an acidified solution of potassium permanganate. This is an element in a compound, which generally means a replacement reaction. But if you're going to have a replacement reaction, the elemental substance has to be more reactive than the substance it's replacing in the compound. Silver is not more reactive than potassium. This is not going to be a replacement reaction. So if it's not one of our obvious reactions we've learned, it must be a non-obvious reaction. And that can either be a Bronsted acid-base reaction or an oxidation-reduction reaction. If you notice the reactants have one of these strong oxidizing agents that we've discussed in class, then it'll be a redox reaction. And this one has the permanganate ion, which we know is a strong oxidizing agent. So this will be a non-obvious oxidation-reduction reaction. And to predict the products, we're going to go to Plan 9 and immediately write the reactants in ionic form. So the silver would be written in its elemental state, Ag+, but the potassium permanganate would be dissociated into a potassium ion and a permanganate ion. And if we calculate the oxidation numbers of all the elements on the reactant side, the permanganate has the manganese ion in its oxidation state of +7, and in an acidic solution, the manganese ion gets reduced down to +2. That's going to be our reduction. If that's the element being reduced, we have to find the only other element in the reaction that can have its oxidation state go up. Can't be the potassium, it's as high as it can be. It's almost never going to be oxygen because oxygen is so electronegative. That leaves silver, and silver could actually turn into the +1 ion. And so we're going to have an oxidation and a reduction occurring here. The reduction is the permanganate turning into Mn2+, and the oxidation is the silver atom turning into the silver ion. To balance a half reaction, you make sure all the elements except for O's and H's are balanced first. And in the top reaction, we have 1 manganese on both sides. To balance the oxygens, you add waters. So we would add 4 waters to the right side in order to balance the O's. And for an acidic solution, to balance hydrogens, you would add hydrogen ions, and we would need to add 8 hydrogen ions to the reactant side to balance the element hydrogen. All elements are balanced now. The only thing that's not balanced is the charge. And on the left side of the equation, the total charge adds up to +7. It's actually 8 plus -1 equals 7. And the right side is +2. So the difference between 7 and 2 is 5. So you need to add 5 negative electrons to the reactant side. For the silver half reaction, silver's balanced. There are no O's and H's. We don't have to add any waters or hydrogen ions. All we have to do is add electrons to balance the charge. And because the left side has a charge of 0 and the right side has a charge of +1, we need to add 1 negative electron to the right side. Now the two half reactions are balanced. In order to add the reactions together, you have to make sure that the electrons gained by the reduction half reaction exactly equal the electrons lost by the oxidation half reaction. So to do that, we'll have to multiply the oxidation half reaction by 5. If we do that and add these together, the reactant side is 5 electrons, 8 hydrogen ions, 1 permanganate, and 5 silver atoms. The product side would be a manganese 2 ion, 4 waters, 5 silver ions, and 5 electrons. The electrons cancel out, and our final net ionic equation is 8H plus aqueous plus MnO4 minus aqueous plus 5 Ag solid yields Mn2 plus aqueous plus 5 Ag positive aqueous plus 4 H2O liquid. The second half of test 4 was on stoichiometry, and so we're going to look at the stoichiometry of chemical reactions. And the first one we're going to do is a 0.479 gram sample of citric acid, HC6H7O7, and in parentheses, its molar mass is 192.1 grams per mole, is titrated with 21.30 milliliters of a KOH solution. Find the molarity of the KOH solution. So if you'd like to pause and take a couple minutes and try to work this out, we'll give you a chance to do that, and then we'll go through the setup. This problem is an example of a titration. You have citric acid, a 0.479 gram sample, probably placed into a flask. Water's added to it to dissolve it. And then in the burette, you place potassium hydroxide solution and you drip it in. And you wind up dripping in 21.37 milliliters until you probably get to a phenolphthalein endpoint where the solution turns pink. From this reaction, we should be able to calculate the molarity of the KOH. The reactants here are citric acid and potassium hydroxide. You should recognize this as an exchange reaction. It's two compounds. So you're going to switch the partners, and if they produce either a precipitate, water, or a gas, then it would be an exchange reaction that's taking place. For the citric acid, there's a hydrogen, and then there's what must be called the citrate ion. It's nothing you've learned before, but if you know that hydrogen ions are +1, then C6H7O7 is just a bizarre polyatomic ion, but it would have to have a charge of -1. So when you switch the partners, hydrogen would go with hydroxide to make water, and potassium would go with citrate, and the formula would have to be K, C6H7O7, because the two ions making up that compound each have charges of +1. So this reaction is balanced how it's written. The next step you do after balancing an equation in a stoichiometric calculation is you write down the given information and what you're trying to figure out. They've told us that we weighed out 0.479 grams of the citric acid. It was probably placed in the flask. Water was probably added to it, but the amount of water doesn't make any difference whatsoever because it's the mass of the solid citric acid that we placed into the flask that we're going to use to convert into moles. All we need is the molar mass. So the amount of water added to the flask, irrelevant in this problem. What are we trying to figure out? The molarity of the KOH solution. That's solution data. And I want you to notice anytime you have solution data in a stoichiometric problem, the solution data has to come in pairs. You have to know the concentration, which is molarity, and its volume. So the volume is 21.30 milliliters, and it's the molarity we're trying to figure out. But the important thing to recognize here is it's two bits of information. The mole ratio between the citric acid and the potassium hydroxide is a 1-to-1 ratio. That's going to be the important middle step in our stoichiometric calculation. So the first step in all stoichiometric calculations is to convert something into moles, and we can convert the 0.479 grams of citric acid into moles. I'll use Ca to stand for citric acid. The problem gave us the molar mass, so we're going to multiply this by the inverse of the molar mass so that the grams of citric acid cancel out. And our first step is we've calculated the moles of one reactant or product. Once you've done that, you can now convert this into the moles of any other reactant or product by using the coefficients in the balanced equation. In this case, it's a 1-to-1 ratio. 1 mole of citric acid always reacts with 1 mole of potassium hydroxide. So to make the units cancel out, I'll put the 1 mole of citric acid on the bottom and the 1 mole of potassium hydroxide on the top. And now I've converted this information into how many moles of potassium hydroxide had to be used in the reaction. If you want to calculate the molarity, the final step is to switch moles into the appropriate units. If you know that molarity is moles per liter, and we want the molarity of the KOH, so we already have the moles of the KOH, we need to divide it by its liters. So I'm going to take my 21.30 milliliters, convert it to 0.02130 liters, and I'm just going to divide by that. No units cancel out. I don't want them to cancel out. I want the units to be moles per liter, and that's what they are. And this multiplies out to 3 significant figures to be 0.117 molar KOH. Let's try one more stoichiometric calculation. Swimmer's ear, trademark, contains H3BO3, which is actually boric acid. In parentheses, its molar mass is 61.84 grams per mole. A 1.47 gram sample of swimmer's ear is titrated with 19.50 milliliters of the 0.117 molar KOH solution. Find the mass percent of boric acid in swimmer's ear. So take a couple moments. Let's see if you can work this out and then come back and we'll go through the problem together. So this is another titration calculation. We have an acid, boric acid in swimmer's ear, that's reacting with the potassium hydroxide. When they react, they're going to switch partners. The hydrogen goes with hydroxide to make water. This is therefore going to be an exchange reaction that produces water, called an acid-base reaction. And the potassium would have to go with the borate. Borate is not a polyatomic ion you've memorized, but if the formula for boric acid is H3BO3, that means you should know that the borate ion's charge has to be -3. If potassium is +1, then the formula for potassium borate must be K3BO3. To balance the equation, we need a 3 in front of the KOH to balance the potassiums, and then a 3 in front of the water to balance the hydroxides and the free hydrogens. So this is our balanced equation. If you're trying to find the mass percent of boric acid in swimmer's ear, we need to know the number of grams of boric acid, and then we're going to divide it by the number of grams of swimmer's ear. If it ever says find the percent of, it's then going to tell you what you're going to divide. Boric acid divided by swimmer's ear. So they've already told us the mass of the swimmer's ear, 1.47 grams. Do not write that under H3BO3. The problem is not telling you there's 1.47 grams of boric acid. They're saying it's 1.47 grams of this substance or this material or this mixture called swimmer's ear. That 1.47 grams will be used in the very final step when we calculate the percent by mass of boric acid in swimmer's ear. The mass of boric acid is what we don't know. That's what you're solving for. What you're given is information about the potassium hydroxide. 19.50 milliliters was used, and the molarity was 0.117, and if I use a guard digit from the previous problem, 0.1171. The mole ratio in this balanced equation is a 1 mole to 3 mole ratio. So the first step in the calculation is to convert given information into moles. In our last problem, we were given the mass of citric acid. You convert mass into moles by using molar mass. In this problem, we're given solution data, molarity and volume of the KOH. If you know molarity and volume, you multiply them together because that gives you moles. The molarity is 0.1171 moles of KOH per liter of solution, and we used 0.01950 liters of solution. The liters cancel out. You now have moles of KOH. That's always your first step. Second step is always the mole ratio step. And to make the KOH cancel out, I'll put 3 moles of KOH on the bottom, 1 mole of boric acid on the top. Moles of KOH cancel out, and we now know how many moles of boric acid must have been in the sample. If I want to know how many grams of boric acid there are, my final step will be switching moles into grams, and grams to moles to grams, always done with the molar mass. That was given in the problem, 61.84 grams per mole. We'll put the mole on the bottom to cancel out, and the 61.84 grams on the top, and we can now calculate how many grams of boric acid there were in the sample from the titration. That comes out 0.0471 or 0.04707 grams of boric acid with a guard digit. The final answer is going to be the mass percent of boric acid in swimmer's ear. So to do that, we take the mass of the boric acid, divide it by the mass of the swimmer's ear, and that ratio multiplied by 100 will become a percent. Because our denominator is 3 significant figures, so is the numerator in this case actually, the answer will be 3 significant figures, and that comes out 3.20% boric acid in swimmer's ear. Test 5 is on gas laws and thermochemistry, so we're going to do some problems for each of those chapters. First, on the gas laws chapter, we're going to see if we can calculate the density of chlorine gas at STP, and the one bit of information I'll need to give you is the universal gas constant, 0.08206 liter atmospheres per mole Kelvin. So take a moment, see if you can work that out, and then we'll go through the calculation. Anytime you're looking for a variable of a gas and you know other variables, usually we do this with PV equals nRT. If you're trying to find the density, though, it's a little bit different. Density is actually mass divided by volume, and PV equals nRT doesn't have mass in it. So we use the alternate form of the ideal gas law equation, PV equals mass over molar mass RT, because if you can arrange this with M divided by V, that's going to be your density. The M, the mass, is in the numerator on the right side. V, volume, is in the numerator on the left side, so I'm going to divide both sides of the equation by V. So the V will move to the denominator on the right side, and I will have M over V. If I move the R and the T to the denominator on the left and the molar mass to the numerator on the left, then M over V, which is density, will equal the pressure of the gas multiplied by its molar mass divided by RT. In this particular problem, you need to know what STP means. That's standard temperature and pressure. So the standard pressure is 1.000 atmospheres. So that's the pressure we're going to use in the equation. Chlorine gas, chlorine is a diatomic substance. Chlorine atoms, which don't have complete outer shells, will always pair together to create noble gas configurations, and they form diatomic molecules to do that. The molar mass of diatomic chlorine would be 70.90 grams per mole. The denominator is going to be the universal gas constant R, and the temperature we're going to use is going to be standard temperature, which is 0.0 degrees Celsius, or 273.2 Kelvin. So when you've set up the problem, the atmospheres will cancel out, the moles will cancel out, the kelvins will cancel out, and the only units left over are grams per liter, which is the units of density for a gas. Solids and liquids are usually grams per milliliter, but gases, because they have such low densities, so you can actually have a more manageable number, they give the densities as grams per liter. And to 4 significant figures, this comes out 3.163 grams per liter. Let's try this. A mixture of 0.400 grams of oxygen and 0.500 grams of carbon dioxide exert a pressure of 3.00 atmospheres. Find the partial pressures of the two gases. Take a minute and see if you can actually do this calculation where you determine their partial pressures. When you have a gas mixture, the individual pressure of each gas in the mixture is called its partial pressure. And the partial pressure is related to the total pressure of the gas mixture and the mole fraction of the particular gas. So we have to calculate the mole fraction of oxygen and the mole fraction of carbon dioxide in this mixture. And if we multiply the mole fraction by the total pressure, that's going to give us the partial pressure. So the first calculation here is to calculate moles of oxygen and moles of carbon dioxide. Oxygen is a diatomic gas. Its molar mass is 32.00 grams per mole. So if we multiply by the molar mass in reciprocal form, grams will cancel out, and we'll have calculated how many moles of oxygen gas are in this particular mixture, which comes out 0.0125 moles. We have 0.500 grams of carbon dioxide. Carbon dioxide's molar mass is 44.01 grams per mole. So multiplying by the reciprocal of carbon dioxide's molar mass, we can make the grams cancel out, and we'll have calculated how many moles of carbon dioxide are in this mixture, 0.0114 moles. If we add those together, we're going to get the total moles of gas in the container, and then the mole fraction of each gas will be the moles of the individual gas divided by the total moles. And that's an important number because that's going to allow us to calculate the partial pressures. The partial pressure of oxygen is going to be the mole fraction of oxygen multiplied by whatever the total pressure is, which in this case is 3.00 atmospheres. So I'm not going to calculate the mole fraction exactly, but just show you how it's calculated. The mole fraction of oxygen is the moles of oxygen, 0.0125, divided by the total moles of gas in the mixture, which turns out to be 0.02386. Divide those to get the mole fraction, multiply it by the pressure of 3.00 atmospheres, which is the total pressure of the mixture, and that's going to give you the partial pressure of oxygen gas, 1.57. If there's only two gases in the mixture, the other one must be making up the rest of the pressure, so 3 minus 1.57 would give you 1.43, and that would have to be the partial pressure of the CO2. But if you want to do it the same way, just to demonstrate this technique one more time, we'll take the moles of carbon dioxide divided by the moles of the total gas. That'll give us the mole fraction of carbon dioxide, multiplying it by the total pressure of 3 atmospheres, and we wind up getting a partial pressure of 1.43 atmospheres for carbon dioxide. Let's move to a stoichiometric problem that involves gases. How many grams of aluminum must have reacted with hydrochloric acid if 275 milliliters of hydrogen gas are collected by water displacement? The water level inside the gas collecting tube is 27 millimeters higher than the outside. Atmospheric pressure is 748 torr. Water temperature is 23 degrees Celsius, and water vapor pressure is 24 torr at this temperature. Take a few minutes now, see if you can work out this stoichiometric problem involving a gas, and then we'll go through the answer in a moment. So in this particular problem, they're describing a reaction between aluminum and hydrochloric acid. This would be a replacement reaction. Aluminum being active enough to replace hydrogen and acids, kicks the hydrogen out, you form aluminum chloride, and then the other product would be elemental hydrogen gas because the aluminum atoms are turning into aluminum ions, which means they're being oxidized, so the hydrogen ions must be reduced down to its elemental form of diatomic hydrogen. To balance the equation, 2 in front of the aluminum, 6 in front of the HCl, 2 in front of AlCl3, and 3 in front of H2. In this particular problem, we're given 275 milliliters of hydrogen gas that are being collected. They want to know how many grams of aluminum must have reacted to produce that volume of hydrogen gas. The mole ratio that we're going to use in this balanced equation is the mole ratio between the aluminum and the hydrogen, which is 2 to 3. So when you have the volume of a gas and you want to stoichiometrically determine how many moles there are, so you can therefore relate it to other substances in the equation, the way you turn the volume of a gas into moles is by using PV equals nRT. So we're going to have to get the pressure of the hydrogen gas, the volume of the hydrogen gas, and the temperature of the hydrogen gas. The temperature is going to be assumed to be the same as the water temperature. The gas is collected in a eudiometer by water displacement. Whatever temperature the water is, that's going to be the temperature of the gas that's touching it. So the 23 degrees Celsius will be the temperature of the hydrogen gas. Its volume is 275 milliliters, but they did not tell us directly the pressure of the hydrogen gas. They told us what atmospheric pressure was. They told us the difference in water levels, and they told us water vapor pressure. So let's draw a picture of what they're describing here. The hydrogen gas is collected in a gas collecting tube, and the level of water is 27 millimeters higher on the inside than the outside. That means the pressure in the gas collecting tube is less than atmospheric pressure. So it's going to be 748 torr minus the difference in the levels. But because torr are the same thing as millimeters of mercury, I can't go 748 millimeters of mercury minus 27 millimeters of water. So the 27 millimeters of water have to be converted into what they would be if they were mercury instead of water, and we get that by dividing the 27 by 13.6. That'll tell us the pressure in the gas collecting tube, but because the gas is collected by water displacement, there will be some water vapor in the gas collecting tube mixed with the hydrogen. We have to subtract the water vapor's partial pressure away so we can calculate the partial pressure of just the hydrogen gas. So that calculation would look like this. Atmospheric pressure, 748 torr, minus the difference in levels in torr, which would be 27 divided by 13.6. That gives us millimeters of mercury, which are the same thing as torr. And then we subtract the water vapor pressure, which was 24 torr. So therefore, the pressure of the hydrogen gas in this gas collecting tube is 722 torr. So now we have enough data to calculate the moles of hydrogen gas, and that's always the first step in a stoichiometric calculation. Determine the moles of something in the balanced equation. So we're going to calculate the moles of hydrogen gas by going PV over RT. The pressure that we just calculated needs to be switched to atmospheres, the volume needs to be switched to liters, and the temperature needs to be switched to Kelvin. If we make those three conversions, then we're going to be multiplying 0.950 atmospheres by 0.275 liters, dividing by R, and dividing it by the temperature of 296 Kelvin. Atmospheres cancel out, liters cancel out, Kelvin cancel out, and the moles are in the denominator under a fraction bar, so they flip to the top, and so our units will be moles. And it's important to realize that we're using the pressure of hydrogen gas, the volume of hydrogen gas, and the temperature of hydrogen gas. So we're going to get the moles of hydrogen gas, not the moles of aluminum. Aluminum was not the gas that made all these measurements. So we've calculated moles of hydrogen gas. That's the first step in the stoichiometric calculation. Second step, mole ratio step. To cancel out the moles of hydrogen, we put 3 moles of hydrogen on the bottom from the balanced equation, 2 moles of aluminum on the top. Moles of hydrogen cancel out. We've now calculated how many moles of aluminum must have formed this amount of hydrogen gas. The last step is to calculate grams of aluminum. That's done by aluminum's molar mass. 1 mole of aluminum on the bottom, 26.98 grams on the top, and we cancel out the moles of aluminum and we multiply out. We've now calculated how many grams of aluminum must have been in that original sample, and to 3 significant figures, that comes out 0.193 grams. Next problem. Under the same conditions, nitrogen gas effuses at 30.5 milliliters per minute, while an unknown gas effuses at 10.9 milliliters per minute. Find the molar mass of the unknown gas. Take a couple moments and see if you can do this calculation based upon Graham's law. So Graham's law states that if you have gases and they're effusing out of a container under similar conditions, which means the temperature would be the same, then that means that the kinetic energy of each gas have to be equal because the temperatures are the same. So I could say the kinetic energy of the nitrogen gas as it's effusing out would be 1/2 mv squared, and the kinetic energy of the unknown gas would be the same number, 1/2 mv squared. Those would have to be equal to each other. If we want to solve this for the molar mass of the unknown gas, I would first cancel out the 1/2s on each side of the equation, and then I would isolate the molar mass of gas X on the right side, so divided by V sub X squared. As long as you can now plug the values into the equation, we should be able to solve for the molar mass of the unknown gas. The molar mass of diatomic nitrogen is 28.0 grams per mole, and the velocity of the nitrogen gas is its diffusion rate, 30.5 milliliters per minute, and we have to square that. In the denominator, the velocity of the unknown gas is its diffusion rate, which is 10.9 milliliters per minute. So the milliliters per minute cancel out. The only units left over are grams per mole, and as long as you've squared the 30.5 and squared the 10.9, you should get a 3 significant figure answer of 219 grams per mole is the molar mass of this unknown gas. Let's add a part B to this problem. The unknown gas from before is found to be 56.3% phosphorus and 43.7% oxygen by mass. Find its empirical and molecular formulas and take a couple minutes and see if you can calculate those two answers. To calculate an empirical formula, we need to start with mass data, and they've given us the percentages of the gas by mass, 56.3% phosphorus, 43.7% oxygen. When you're given percents, you assume you have a 100-gram sample of that material. And if you do, it would therefore be 56.3 grams of phosphorus, 43.7 grams of oxygen. To do an empirical formula determination, we want to know the number of moles of atoms of phosphorus and the number of moles of atoms of oxygen. So I'm going to use the atomic molar masses to convert these into moles. So dividing by the molar mass of atomic phosphorus, I get 1.818 moles. And I'm trying to calculate how many oxygen atoms are in the formula. That's why I use the molar mass of atomic oxygen. This will tell me that there are 2.73 moles of atomic oxygen in this 100-gram sample. Once you've calculated the moles of the two, you divide them both by whichever is the smaller number, which is the 1.818, and hopefully you'll get a nice simple integer ratio. In this case, we get 1 mole of phosphorus to 1.5 moles of oxygen. The 1.5, however, is not within 1/10 of a mole of an integer, so the fact that it's so far away from an integer, we cannot assume that's because of experimenter or experimental error. So what we're going to do is we're going to multiply both these numbers of moles by integers until we can make them close to integers. If we multiply them both by 2, this becomes 2.00 moles of phosphorus and then 3.00 moles of oxygen, which are now both exactly integers, certainly within 1/10 of a mole of an integer. So we can assume that this compound is 2 moles of phosphorus to 3 moles of oxygen, and whatever the mole ratio is, that has to be the atom ratio as well. So therefore, it's 2 atoms of phosphorus to 3 atoms of oxygen. That's your empirical formula. To get a molecular formula, we need to calculate the molar mass of our empirical formula P2O3. So to do that, we're going to take 2 moles of phosphorus, multiply by 30.97 grams per mole. That comes out 61.94 grams. And then we'll take 3 moles of oxygen multiplied by 16.00 grams per mole. That comes out 48.00 grams. Add these up, and the molar mass of P2O3 is 109.94 grams. Now, the real molar mass of the compound we'd calculated earlier was 219 grams per mole. So we're going to divide 219 by the empirical formula's molar mass of 109.94. And this number has to be close to an integer. If it's not close to an integer, it just means either really bad experimental data or you've made a mistake. But whatever integer this is closest to, in this case it comes out to be 2, that means this is what you have to multiply the empirical formula by to get the true molecular formula. So multiplying the empirical formula by 2, we would get a molecular formula of C4H6. The second chapter we had for test 5 was on thermochemistry, so we're going to finish with a couple of thermochemistry calculations. The first one is an experimental calculation. 10.0 grams of sodium hydroxide are dissolved in enough water at 24.5 degrees Celsius, and the temperature reaches 47.6 degrees Celsius. If the solution's mass is 110.0 grams, and the solution has a heat capacity of 4.184 joules per gram Celsius degree, find the heat of the reaction in kilojoules per mole of sodium hydroxide, and take a couple minutes and work that calculation out, and then we'll go through it together. In this case, the reaction that's occurring is the solid sodium hydroxide is dissolving in water. So when sodium hydroxide dissolves in water, it looks like, because the temperature of the water is going up, this is an exothermic process. So we want to calculate the heat change associated with this particular reaction. The way we do that is we actually do not measure the heat of the reaction. We measure the amount of heat that water in a calorimeter absorbs. And we do that by using water's heat capacity, its mass, and its change in temperature. So the heat gained by the solution, which is mostly water, will be the heat capacity, 4.184, multiplied by the mass of the solution, which is 110.0, multiplied by the change in temperature of the solution, which is always final minus initial. So 47.6 minus 24.5 turns out to be positive 23.1 Celsius degrees. The grams cancel out, the Celsius degrees cancel out, and we get our answer in joules. So we will have calculated that the water in this calorimeter absorbed, because it's a positive number, 10,600 joules. The key point in a calorimetry calculation is if you have a good calorimeter, the water absorbed all the heat from the reaction. So whatever amount of heat the water absorbed, the 10,600, that's exactly how much heat the reaction gave off. Algebraically, that just means the Q of our reaction is just going to be the negative of whatever the Q of the solution is. So the negative of positive 10,600 is negative 10,600 joules. So this is the amount of heat released by the sodium hydroxide dissolving in the water. That number in and of itself is not very informative. If we want to make it informative, we've got to divide it therefore by the moles or the mass of a reactant or product in our equation. And in this case, we want to know what the value is per mole of sodium hydroxide. So sodium hydroxide happens to be a reactant in this reaction, and so it all reacted away, all 10 grams, so that actually makes the problem a little bit simpler. We don't have to do a balanced equation and calculate how many moles of products were produced. If you want to know the heat of the reaction per mole or per gram of a reactant, you just take how much of the reactant you know reacted away, in this case 10 grams of sodium hydroxide, use its molar mass to convert the grams into moles, and we calculate that this calorimeter had 0.250 moles of sodium hydroxide dissolving. So we take the negative 10,600 joules divided by the 0.250 moles of sodium hydroxide. If we want it in kilojoules per mole, I'll need to do 1 metric conversion. 1 kilojoule equals 1,000 joules, so I'll arrange it with the joules on the bottom to cancel out. And the final answer comes out negative 42.5 kilojoules per mole of sodium hydroxide. Final problem will be a theoretical calculation. I want you to calculate the standard heat of combustion for C2H6 gas in kilojoules per gram of C2H6. Now this could be done experimentally in a bomb calorimeter, or it could be done theoretically by using bond energies, or it can be done theoretically by using standard heat of formations. And I'm going to want you to do it the latter way. So from handout 9 on our class website, I'm going to give you the standard heat of formations for C2H6 gas, for H2O gas, and CO2 gas, and have you take a couple of minutes to try to calculate the heat of combustion for C2H6 in kilojoules per gram. So when using standard heat of formations, the technique is to take the standard heat of formation of the products and subtract the standard heat of formation of the reactants, and that will give you the enthalpy change for the balanced equation that you have written. So what balanced equation are we going to use? Well, C2H6, if it's undergoing combustion, will react with O2 to form CO2 and H2O. If you balance the equation with all integers, the reaction will come out 2 C2H6 plus 7 O2 yields 4 CO2 plus 6 H2O. So what we're going to do is, by using the standard heat of formations, we're going to calculate how much heat is released or absorbed when you combust 2 moles of C2H6. So the technique is starting on the product side and using the heat of formations of the products, and then subtract the heat of formation of the reactants. We have 4 moles of carbon dioxide, so I'm going to go 4 moles multiplied by the standard heat of formation of CO2, which is negative 394. Then we also have 6 moles of water, so I'm going to go plus 6 moles of water multiplied by its standard heat of formation of negative 242. All the products are done. We now go to the reactant side, and we're going to subtract their heat of formations. So I'm going to go minus 2 moles of C2H6 multiplied by its standard heat of formation of negative 85 kilojoules per mole. And then we have to go minus 7 moles of oxygen multiplied by its standard heat of formation, which I didn't give to you because I expect you to know that an element, how it exists naturally on Earth at room temperature and room pressure, would have a heat of formation of 0. And so this is technically 7 moles of O2 multiplied by 0 kilojoules per mole. In each of the 4 terms, the moles cancel out, and so we're going kilojoules plus kilojoules minus kilojoules minus kilojoules. Our answer will just be in kilojoules. And because each of the standard heat of formations were given to the ones place, and this is a giant addition problem, my answer will be accurate to the ones place. I get negative 2,858 kilojoules. That's how much heat is given off when you combust, what's in the balanced equation? 2 moles of C2H6. So that's the amount of heat given off per 2 moles of C2H6. So I can write this negative 2,858 kilojoules per, from the balanced equation, 2 moles of ethane. If I want it in kilojoules per gram, I will have to switch the moles of ethane into grams of ethane, and I'll do that with ethane's molar mass. A mole of ethane is 30.08 grams. I'll put the mole on the top so it'll cancel out, and the gram on the bottom, and I will now have my final answer at 4 significant figures. It'll be kilojoules per gram of ethane, so therefore we've calculated theoretically that if you combust 1 gram of ethane, it will release 47.51 kilojoules.